Got a special shirt for this month's Math Counts Mini from my man Bob Fisher out in Indiana. He's been coaching Math Counts since way back when I was a student. That's a long time. Now he's coached some national champs, so I hope some of that rubs off on me because I've got 3 pretty tough geometry problems here. Now geometry, you know what that means. I got my secret weapon right here, my man Harvey. How's it going, Harvey? Yeah, I got 3 geometry problems this month, all right, Harvey? But the first 2, I got them. I can take care of them all by myself, but the third one, I'll admit it, right up front, I'm going to need your help. What's that? Oh, you think I'm going to need my help on the first 2? Well, you just hang out right over there, all right? And if you have anything clever to say on the first 2, you just oh, you already have something. Hold on, Harvey. Let me try it myself first, all right? Here we go. Here's our first problem. We're going to try to solve this without Harvey. Then we'll let him jump in. We got a trapezoid right here, A, B, C, D. AB is parallel to CD. The diagonals intersect at P, and we're told that the area of this little triangle up here is 16. And the area of the larger triangle down here is 25. And we want the area of the whole trapezoid. All that means is we just have to find the areas of these 2 little triangles out there, and we're all set. Let's see, where do we start? We have a trapezoid that gives us parallel lines, and parallel lines means similar triangles. These 2 triangles are similar, and we already have their areas, so we know the ratio of their sides, because well, the ratio of the areas of 2 similar triangles is just the square of the ratio of corresponding sides. So ratio, the areas is 16 to 25. That means the ratio of corresponding sides is 4 to 5. So this to this is 4 to 5. This to this is 4 to 5. This to this is 4 to 5. How's that going to help? It's time for one of my favorite geometry problem-solving strategies. Right here, we have a problem about areas. We have a couple triangles right here that have sides, BP and PD, that are along the same line. Now check this out. Let's look at the areas of these 2 triangles. They share an altitude from A. And that means that the ratio of the area of this triangle to the area of this triangle is the ratio of this base to this base. Because to get the areas of these 2 triangles, we're just going to multiply this base by that altitude, and then divide by 2, multiply this base by that altitude, divide by 2, you have the same altitude. So the ratio of the areas is just the ratio of these 2 bases. And we know what this ratio is. We figured that out already from our similar triangles. Ratio of corresponding sides of these 2 triangles is 4 to 5. So now we know the ratio of this area to this area is 4 to 5, which means this has area 20. We do the same thing over here. You got a strategy that works once in a problem but doesn't quite finish it. Run that back, do it again. We do it again over here. The area of that is 20 as well. So now we've got the area of the trapezoid. 16 plus 25 is 41. Add on the 2 20s and we get 81. We're finished with, what? Oh, you had that a long time ago. What, it's just 4 plus 5 and then you square it. What? Yeah, 81 is 9 squared. So, oh, wait a second. If 16 up here, that's 4 squared. 25 here is 5 squared. And you're telling me that you then just take the 4 and 5, add them, and then square it, and you get the right. Well, it works here. That always works? No. No. Okay. Oh, that's... Wait a second. I'm going to give you a little homework, all right? Harvey's telling me that in this problem, he just looked at this and he said, okay, this is 4 squared, this is 5 squared. And then he just adds 4 and 5 and squares it and gets the right answer. And it does get the right answer, but he's telling me that will work whatever these 2 numbers are. I'm not sure I buy it. So here's your homework. Try to prove Harvey wrong. What? Oh, nobody proves Harvey wrong. All right, try to prove that Harvey's right. All right, prove that if you start with any 2 numbers here and here, any 2 positive numbers, you take the square root of this one, square root of that one, add those 2 results, and then square your sum, and you'll get the right final answer. I'm a little suspicious of that, but Harvey's usually right. But, oh, yeah, okay, whatever. We're going on to the second problem. Here we go. Oh, that looks like Charlie Brownlee's triangle, man. What do we got here? We got triangle ABC. We divide each of these sides into 4 equal pieces, and then draw these little lines and make these little shaded regions. All right, grab my pen and get to work here. Well, first of all of these segments here, these are parallel. We have some similar triangles here, and we can see that with a little side angle, side similarity here. This is a quarter of this. This is a quarter of this. And of course, we have the same included angle here. So the little triangle is similar to the large triangle. Of course, we can do the same thing here. This triangle is similar to the large triangle. This triangle is similar to the larger triangle, and so on. Now, this side length is 1/4 of the whole thing. So the area of that itty-bitty triangle is the square of 1/4 is 1/16 of the whole thing. So this little triangle is 1/16 of the whole thing. But what about this region down here? How are we going to deal with that? That's not just a triangle, but it is what's left if you start off with this triangle right here. Cut that triangle out of this bigger triangle. So let's start off by looking at this triangle right here, and its side lengths are 3/4 the side lengths of the big triangle. So the area of this big triangle is the square of 3/4 is 9/16 the whole thing. And then we're going to subtract off, to get this region down here, we're going to subtract off the area of this triangle. And the sides of this triangle are half the sides of a large triangle. So its area is 1/4 the area of the whole big triangle. So this piece down here, we just subtract. 9/16 minus 1/4. Well, 1/4 is 4/16. That gives us 5/16. So we take the 5/16 of the whole triangle that's here, add it to the 1/16 of the triangle up there. That gives us 6/16. Simplify that, and we get 3/8. And so you got a smart way to do that one? Of course you do. What is it? Well, it's 6 little triangles out of 16 little triangles. It's obvious, and you're done. What? Oh, that's really clever. Check this. You're gonna like this. I actually understand this one, so check this out. We've got a little triangle up here. Now we can come down here, and we can break this into little triangles as well. You're going to take the little midpoint down here and go doink, doink. These are midpoints up here. So this splits this triangle into 4 congruent little triangles. Well, now we just take these little triangles. We keep going down here. Doink, 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 doink. All these little triangles are congruent. Keep on going. Doink, 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 doink. And there we go. Break the whole thing up into 16 little triangles. 1, 2, 3, 4, 5, 6. We got 6 of these little triangles out of these 16 congruent triangles. So the shaded region is 6 out of 16. That's 3/8. That's pretty slick, Harvey. This is why we keep you around. All right, here we go. Last problem. And yes, Harvey, I'm going to tell you right up front, I need some help on this one because that's scary. What we're starting off here is with a frustum. All right, we start off with a frustum, and we're given the radius of the top piece is 8. Radius of the bottom piece is 12, and we're told that this length right here is 15, and we want to find the volume of this frustum thing. Now I know there's this wacky formula, and Harvey probably knows this wacky formula for finding the what? Oh, you don't need to know the formula because you can just prove it whenever you want it. That's great, Harvey. I think there's a wacky formula, but I'm too old to remember those sorts of formulas and things. So. What are we going to do? What? Use the cones. It's a frustum, Harvey. Read the problem. This isn't a cone. Where do you see cones? What's a frustum? Well, Harvey, a frustum is just what you get when you start with a cone and you chop a little cone off the top. Oh, those are the cones. Okay, Harvey. We'll start with the cones. That's really clever. Check this out. How do you make a frustum? You start with the cone, and then you chop a little cone off the top. So we're going to start with the cone. We'll extend this up here, and pretend we start off with a huge cone, and we chop the top cone off. And how are this little cone up here related to the big cone? The little cone is similar to the big cone. Oh, that's really clever. So we just continue this all the way up. And, well, we've got similar cones. We also have some similar triangles right here. Parallel lines, similar triangles. We have parallel lines right here, 8, 12. And now we know the ratio of this triangle to the larger triangle. Ratio of the corresponding sides is 8 to 12 is 2/3. So now we see that the little piece, the piece that we cut off here, its height is 2/3 of the whole thing. So the ratio of side lengths of our little cone to our big cone is 2 to 3. And that means that the ratio of their volumes is the cube. of 2/3. It's 8 to 27. So this piece that we're cutting off is 8/27ths of the whole thing, of the whole big cone. So that means that what's left over is, let's see, 27 minus 8 is 19. This piece down here is 19/27ths of the large cone. Well, now all I have to do is find the volume of the whole big cone, and then take 19/27ths of it, and I can handle a cone. So I don't have to think about the frustum anymore. I've got the radius of the base of the cone. Now all I have to do is find the height. I've got this piece right here. This is 12, this is 15, so this is 9 right there from the Pythagorean theorem of 3, 4, 5 right triangles. So to get the height of the whole large cone, all I have to do is figure this out, and that's a job for similar triangles. So we got this triangle is similar to this one, so we know that, let's see, we got x over x plus 9 equals 8 to 12, which of course is just 2/3. So I'll just multiply both sides by 3 and x plus 9. We get 3x equals 2x plus 18, which tells us, of course, that x is 18. And now I can find the volume of the whole large cone. And the volume of our frustum down here is just 19/27ths of the volume of the whole cone. So the volume of the whole large cone is 1/3 times square of the radius, 12 squared, times the whole height, which is 27, times pi. All right, so our 27s, they cancel out. 3 cancels and knocks out a part of one of the 12s, leaves us 4. Oh boy, 4 times 12 is 48. So I've got 19 times 48 pi. Well, to calculate that, 20 times 48 is 960. We want 19 times 48, subtract 148, we get 912 pi. And we're finished. Thanks a lot, Harvey.